Hello everyone, welcome to Connection Wednesdays. Today is September the 19th and we have the second Connection Wednesday from the autumn season. Today we will present you another great example of a steel connection modeled, analyzed and checked in IDEA StatiCa, and it will be a welded frame corner arch with openings. So before we start, let me mention some practical things. You are muted by default and you can communicate with us via question panel in the GoToWebinar platform. So please feel free to write your questions. We will try to answer them during the webinar, and also if we don't have enough time, we will send you an email. My name is Jana, and together with Adam, we are both product engineers at IDEA StatiCa. And what will you see today? So it will be, as I mentioned before, project of our customers, the welded frame corner arch with openings, and in the end we will discuss some results. Last time you asked about some questions about buckling, so today we will focus on that and we will try to present you how to work with the buckling analysis. In the end, we will have a short question and answer session. And now I think we are ready to pass the presentation to Adam, who will show you step by step how to model the connection. So Adam, the floor is yours.
Thanks, Anna. Hello. Hi, everyone. Welcome once again to the show. Just take the presenter and show my screen. So today's project is a arch frame, interesting shape, first time done in IDEA StatiCa, but never say never, what is possible or not. So this is basically a project that was done on a Czech Technical University in Prague for some of their research on steel structures. So this is some basic drawing that we got. So basically we're just going to model this and check it according to the code in IDEA StatiCa. So let's get started. I'll go to IDEA StatiCa connection and select some starting topology. I leave the material of 355 and pick the Eurocode, since the project was created in Czech Republic in Europe. All right, here we have the basic topology starting with, and we'll just modify these two members. So let's assign new cross section to this member, IP 300, and I'll change the same cross section to this member as well. Fine, and I will move them to create space for the main plate or the main arch of the connection. So I'll just move them along the x-axis, and now I will add the or model the central area. But before that, let me check that's all from the geometry here. For now, I'll just slightly change the angle here to 8 degrees, and that'll be fine. So before we start modeling the joint, I'll just make a short stop at the load effects. This is empty, of course, so we have to define some internal forces of the node of the corner of the arch. First thing I will do is to check the loads in equilibrium. This is what we always should do. And then I have prepared a set of internal forces here, and I will just copy paste them or import them to my model by clicking this Excel import, copy paste those loads, replace the existing 0 set of loads, and they're all there. Okay, that was for the internal forces or the load effects. And let's get started. The modeling. So first, what I will do is to model the two, let's say, members or main plates that continue from this B and C members. And for that, I will use an operation, stiffening member, right? So as we discussed previously, stiffening member is actually you create a member, as in the geometry, but this cannot be loaded by any loads directly. And it's easier to work with all the operations and so on. So this is perfectly the place we use this operation instead of creating another member. So here I will just, of course, change the cross section. I'll define a new one from this welded composed, this T profile, and modify its parameters. So this will be 600, 10.7 to align with these IP 300 members. This will be 150 and this 7.1. All right. Next, to make it slightly bigger, okay, I will click here, change the origin to member, assign it to the member C, that's the column. And here I will leave the bottom flange, set it as type widener, location center, edge index number 1, that's correct. I will also turn off the welds here because I'm gonna work with that later to weld it all together. And one last thing is I'll click here mirror by epsilon or y-axis to get it in place. So this is all perfectly aligned. I will do the same for member B. Of course, I will help myself with the copy command, the best command in IDEA StatiCa. For lazy, or others would say effective users. So let's just slightly modify this and change this to the flange, and we're done. Okay, basic shape, looking good. So let's continue. I will add another operation that will be a stiffening plate. Okay, so the thickness of that will be 10 millimeters. I will change the size of that to 75. And as you might see, it's appearing there. And this is going to be this central connecting plate in the corner. So let's rotate that, and it's in place. Okay. So next one, I will add 2 more stiffening plates now. So let's do that. That will be the connecting plates of these members B and C. So again, thickness of 10 millimeters, fine. I will change the size of that. And origin will be now to the member B and web, and this is going to be rip. In the front side, again and again, I'm going to turn off the welds here. I don't have to turn the welds off here in this stiffening plate because it's assigned to the origin of joint, so there's nothing to weld it to. So here I have to turn it off because it's assigned to the B member. Fine, this is looking good, all aligned. So again, just copy this for the member C. I can just select it like this, and that's it. Again, looking fine. So next, we'll add another stiffening member. So let's click new operation here, and again I will choose this one. And now we're going to model this arch or this circular rounded shape blades that create the arch. So how can we do that? That's a kind of tricky stuff, a secret tip that we're giving to you today. So we have to define the cross section, right? So let's add a new one, and here I will go to the conformed and pick the general shape. Fine. So this is looking like just a simple plate, but here we can start with defining the thickness. Inner radius we leave at 5, and here we can edit the center line. That's what we're interested in. So let's do that. Here we can manually define our point like this. Okay, and just, you know, assembly the whole shape, or again, to the more effective designers like me, for example, that always find the easiest way to move along. I can click on DXF and just select the prepared polyline that was already drawn, and just import that here with this import tool of DXF. So what we do here, what we can see, first thing, we just align the units. Because the drawing is in millimeters, I need to switch to millimeters here. Then I just click on the line here. I click on consecutive to get it all red. That means all is connected and selected. Then I click select to load it into IDEA. That's it, and OK. And fine, I get it loaded here. I get all the points here. Just import it from the DXF. So let's click OK, and OK again. And we've got something here. Good. So next step is just to set it into the right location. So that should be simple now. So let's do that. Of course, I'll put it on the member C, and set it to the top flange as a widener, and now it's looking already good. Okay, and again, I'll just turn off the weld here, the welded connection for now, because I'm going to do that a bit later with another operation. Okay. Oh, I see it. Just I forgot to align the width, and that's it. So that's the first half. Okay, so better than trying to hit the edge here of the another member. tip is to do it in halves and meet here in the center point, which is easier to model. So that's what I'm doing right now. So I'll just copy this one and set it for the member B and copy it for the other member. Okay, and here just click mirror Y and got it right in place. All looking fine. This is just overlapping here, but no worries. We're going to shape that in the next operation. So let's get to that. We start cutting all those plates and members and welding them together to get the final design. So first I will select here the member SM1 and I will cut it by plate SP3, that's this one. Now it just disappeared, but no worries. We'll put it here again, just selecting minus here, and we've got some weld here, and I would like to have a butt weld, of course, so I'll change it to this one. Okay, we can just make sure the weld is there. You see the yellow rectangles, those are the butt welds. So first cut. Now there will be a lot of cuts and copies, right? So I'll copy this one, assign to SM2 and SP2, which is this end plate, the B member. Also cut and weld it. Then I will copy again this operation, and this time I will cut the SM1 by SP1, that's the corner plate. Okay, again it disappeared, but I'll just switch to plus here, and we've got it here as well. Of course, simple copy, select this one, and we've got the cut here as well. Let's check the welds. All in place, all welded by butt weld. Great. So we're getting to the point. Couple of more cuts. So let's copy for cut number 5, and this time we'll be cutting SM1 by this SM3 member, that's the arch, right? And here we have to switch from bounding box, which is a rectangular shape of cutting, to surface, which is driven by the shape of the cut member. So again, this is done. Butt weld in position, copy this for DSM2, and of course I changed this to this one. Okay, this is already looking quite fine, just we have to struggle with this point. No problem. So I will add a new operation now, and that will be a cut of plate. So we'll be cutting now just a plate, and that will be this plate, which is plate or web number 6 of SM3 member. Yeah. So this SM3 member is created of 1, 2, 3, 4, 5, 6 webs, and we'll be cutting the web number 6. So let's select it here, SM1, SM3, web number 6. Okay, this is already doing something here. So I'll just make it correct. So here I'll leave plus, and I'm cutting by SP1, that's correct. and here I changed to minus to get it cut by this left edge, or the left surface of the SP1 plate. And we have the corner weld or a fillet weld, so of course I changed to butt weld. This is all welded in the factory by butt welds, or all prepared. So this is cut, and of course now copy and just change this to SM4, Web 6, okay, and SP1, and I change here the surface of SP1 to the right side, and again welded by butt weld. Good. So that would be it for the cutting, and the last thing, but not least, that makes this design much more attractive are those rounded openings in these two massive webs of the corner. So let's do that. I'll add an operation. Of course, it's called opening. What could that be? Let's see. So I'll select first SM1. So we've got a hole here. That's good. And I'll just modify it to the shape I like, or the shape that was drawn on the draft I showed you. So this is in position, and I would like to add a stiffener to that. What is that? That is actually cut tube that is inserted and welded into the hole. Okay, so you can edit by clicking on this, and here you can set the thickness of it. I'll change to 5 millimeters, and the width, which is of course the length of the tube. If I make it longer, so visible, so it's like this, but I will leave it just as this, 80 millimeters. Okay, and again, just switch to butt weld. Good. Now, of course, copy, of course, change SM2, and done. Now, of course, copy, because there is another pair of holes. I'll change to SM1 now, and just change the size and position, and slightly add some eccentricity, and we're just in position, right? So that's looking good. Now, of course, copy, one magic trick, and done. So that's it. We've modeled this super attractive rounded arch. So now let's calculate that. So now, nervous second, let's see what will happen. And to my, and for sure also yours, surprise, we've got something wrong. There's a singularity. What's wrong? The model is not working, but I'm not that as a surprise, because of course I've prepared this just to show you the function that's called the singularity show up, or how we can call that. Basically, the software shows you what's wrong in your model. So if you go to check here, you can see there's a singularity on member B, because since I did it in a very fast way, and all these copies, etc., I forgot to connect these main members, B and C. These are not connected to the end plate. So let's fix that. Okay, so I'll just in an operation, a simple cut, and select these parts here, B member displayed SP2, and I will leave the fillet welds here. Just change the thickness to 8 millimeters and select the web as double fillet weld to have it on both sides. Good. And just copy this, of course, another copy of copy, and select the member and plate like this. Good. So another try. No, you can trust me. This is going to happen, to calculate. Just maybe to cut the time that we'll be observing the iterations. I have it already. Oh, that was quite fast, so I don't have to switch to already calculated project that I have opened here. So, okay, we have it done, all calculated, all checked. Let's see the results. All is green, that's good. That means we passed the code checks. We can see briefly the overview here on the left side of the 3D screen. Welds are almost at the limit, 98%. This is for this weld, which is colored in orange color. That means it's between 95 and 100% of its capacity. So this is actually quite a good design, pushed to the limits of this joint. So if I go to check, we can browse the results more precisely. For example, if I click on this orange weld that is on the limit, it just takes a second because my computer is not that fast. And that will just open the welds tab and highlight this weld and shows us the information. Okay. Still waiting for the CPU. Okay. So this is the list of all welds. There's quite a many. And here is the one that we are interested in, the orange one. If I click on that, or I can also click on this one to get it highlighted. We've got all the values here, all the checks. You can open that, show more information, what is behind the code check, and what all these numbers means. And of course, we can then browse the results as the strain check, see the stress distribution along the joint. And so that's the stress, and see the trend of deformation. If I would just multiply the deformation display, we would get something like this. So this is 30 times multiplied deformation display. Well, okay, I think I've consumed a lot of time, actually all the time, so I'll be a bit late today, but no worries. I'm just giving presenter to Jana, who's going to discuss more about the results of this example.
Okay, thank you, Adam. It was really a complex connection, and we had a lot of questions. Thank you for that. It looks that it was really interesting connection to present, and also you have some nice comments about you, Adam, so you can have a look at them as well. And now I will just quickly go through some buckling results. You also ask about that quite often. So as you could see, if we just press the simple or the elementary calculate button, we will perform the stress strain analysis. But if we want to start buckling analysis, we have to go to check, tap, and open the calculate button and start the buckling analysis, which is the second line. We don't perform it in the elementary stress strain analysis because it takes, of course, some additional time. So if you are interested in buckling results, just simply open the second line of the button. And you can see we have to wait a while. Okay, and now what's here at the first side is some result for buckling. We don't have the comment that it's not performed anymore, and we have some number. So what is this number? You can also see another tab was added in this top ribbon of the left tables. So I will just open this tab, and you can see we have a table of some shapes and some buckling factors, the factor of the critical load. So what is this factor? It's basically a ratio between the elastic critical buckling load and the applied axial load. So you can see that our factor is about 7. It means that the critical buckling force is about 7 times greater than the force that we applied. And IDEA StatiCa always presents only the six buckling shapes. Of course, there are many more of them. And if we want to present them, we have to click on the buckling shape in the top ribbon. And you can see we have the buckling shape of the first mode. To this shape, the factor 6.67 corresponds. The second shape looks like this. Then the third shape, we have to wait a while. Okay, you can see that we have different critical places around that corner and some more farther shapes. You can see we have some buckling of the web of the column as well. And the number 6 is here. Okay, we always present the results for the extreme load. If you have more load effects and you are interested in in some of them, you have to change this for extreme to for current. In our example, of course, we have only one loading case, so we cannot really choose. But if you have more of them and you are interested, you can change it in the top ribbon. Okay, and the difference of the buckling analysis compared to stress strain analysis is that we don't really provide any pass-fail result or some decision about if it's good or if it's already not good. So we have to discuss a little bit the buckling factor, or the factor of the critical force, as it is correctly called. And actually these values, or the value that you have to fulfill, is defined for different codes, and it's a little bit on the decision of the engineer. So for example, for Eurocode, it has to be greater than 10 for the elastic analysis. And for example, for stiffeners or column panel in shear, while for the plastic analysis, it should be greater than 15. sometimes if you perform some more accurate analysis, like the second order analysis, then you can go a little bit lower with the factor. It has to be greater than 3, but it is really about knowing more about the construction, and so we provide the critical force factor, but the engineer has to decide if 7 is enough or it has to be greater than 15. I want to show you that we have the FAQ in our resource center. I will probably just go directly on our web page. In the top ribbon, you can see resources, which is the center of all the documentation for IDEA StatiCa. In connection and FAQ, you can see, check and report, and how to evaluate backlink results is one of the topic, and it's explained about everything about the backlink analysis, about those factors, and of course in our theoretical background, sorry for that, once more, theoretical background, for example, Eurocode, you can press stability analysis and also read something more about the backlink factor. Okay, I'm not sure if probably I already mentioned everything. Yeah, maybe one more thing. We've also prepared another example that if this factor is not enough for the engineer, he can use this information about the critical place. And in this example, we could just simply add some stiffeners here and here. So I will not do it, and but we have prepared already modified connection. You can see we added 2 stiffeners, one in this place and one in the top place. And I have already performed the backlink analysis, and you can see that it really, the factor is much higher. We can present the backlink shape. And you can see that this place and this place are not critical anymore. So this is the way how you can work with the backlink analysis. Okay, yeah, we are today a little bit longer than usual, but it was a really nice example, and I hope you will not think about that as lost time. About the questions, I know we had some question. I will maybe just mention the one about the internal forces. You asked where is the actual location of the internal forces. So it's always we always define the load at the node. So you enter the internal forces at the node, and from that place, these forces are transferred till the ends of the members by special rigid links, and we load all that connection, and the forces are transferred through all the plates as the FEM analysis, as the usual FEM analysis performs. Okay, so I think the rest of the question we will have to answer them by email, unfortunately. Thank you for your attention. Before we finish, just let me mention that you will be asked to fill a short survey. So please give us some feedback about the webinar, what you would like to see, and etc. And also the recording will be sent to you and about 2 or 3 days after the webinar. It will be available on our YouTube channel as well. If you are not a user of IDEA StatiCa yet, So you can, of course, get a trial version on our web page, and I already showed you the resource center where you can find everything. We also have another webinars. Soon we will launch the invitation for our release webinars, because in October we will release a 9.1 version of IDEA StatiCa, so you can look forward to seeing new features and a lot of improvements. We will make a webinar just about these new features for steel as well as for concrete. And last information, next Connection Wednesday will be on the 3rd of October. And I guess I don't have anything more to say. So thank you very much, and see you next time.
I think that was pretty a lot to say. So thanks, Jana, and looking forward to meet you in 14 days. Bye-bye. Have a nice day.